Hi everyone, thanks for joining. My name is Alex. This is joint work with Owen Eckart, who is a third-year undergraduate student at Purdue, and Paritosh Verma, who is a third-year PhD student at Purdue. Paritosh was supposed to present, he's light in fact, but he had a minor injury that is minor but major enough that he couldn't travel to EC. But he'll be grad in a few years. He's not quite on top. Okay, so fair division, that's the topic of this session. The problem we study in this paper is the standard one, okay? So I have agents with additive purposes, I have items, I want to allocate them, and really we're considering all four possibilities: goods, chores, divisible, indivisible, okay? I want to do it all. And our goal is to be fair and efficient when we allocate these items. What's fair for every one of the four subcases? There's standard notions. For divisible, we just saw envy freeness. I like my stuff more than yours. Proportionality, I like my stuff and the whole thing. For indivisible, EF1 is the standard one. I would have liked my things if I could go and break one of your items. Prop one, I would have been more than an nth if I could include one item I don't have. And the equivalent things with chores. So in chores, we don't have values, we have costs. And so, in energy fee allocation, my cost is smaller than my cost. So on. The EF1 perhaps is the one you haven't seen before. The thought experiment there is I would have preferred my bundle if I could not do a chore that I'm doing. Good. What about efficiency? Pareto optimality is the standard thing. There's no other allocation where everyone is strictly happier and one person is strictly happier. Sorry, weakly and strictly. You know what I'm saying? Fractional Pareto efficiency, same thing, but with respect to fractional allocation. Another fractional allocation where this is true. Okay. Fantastic. How would you approach this problem? Arguably, the most natural way you would start thinking about approaching these things is through welfare functions. So you would say, let's try to maximize a function of the utility. Okay. Let's try to and for the case of cost, let's try to minimize a function of the utilities. This approach is quite fruitful. So one can think of the p-mean welfare function family, and the reason why this family is cute is because it captures pretty much anything reasonable that we would think of. So for p equals 0, for p equals 1, you would say I want to maximize the sum of utilities, or minimize the sum of costs. For p equals minus infinity, as our p approaches minus infinity, egalitarian, right? I want to maximize the minimum utility. For plus infinity, and in chores, you would say I want to minimize the maximum cost. For our favorite Nash, the middle, I want to maximize the product of the utilities. Okay. Now, what is known with respect to this big family of functions and fairness and efficiency? So, okay, observation, they're all efficient, right? By design. Yes, monotone functions of the utilities. You're going to get efficiency for free. So fairness is the only thing to ask for, really. So what is known? For divisible goods, it's been known for a while that maximizing Nash welfare, so the product is PONEF. This is by variant in 74, which I guess is 50 years ago. And the reason the proof is quite insightful, actually. It's equivalent to something called competitive equilibrium of equal incomes. So there's a marked interpretation of the solution that allows us to show the envy-freeness property. For indivisible goods, same rule works. It gives you PONEF1. This one that the Light Prize this year. Congratulations to the authors. One of them is here, Ariel Prakacha. And there's a recent result, beautiful result by Owen and Soxampong, that this is the unique welfare rule that does this, that provides you this EF1 problem. Okay. And nothing else does it. Okay. That's the only P out of this and in the real line that will give you these nice problems. What about chores? Well, for divisible chores, CI doesn't really, doesn't really correspond to the global optimum some objective. And minimizing P mean welfare is unfair for all P. Okay, so no P works for chores, for divisible or indivisible. So for indivisible, you can get EF1 or prop1 or anything by doing something in that family. In fact, it's a minor thing, but we do show that a robust version of these. Okay, so like even beta prop, beta EF1, beta prop k, beta EFK, you cannot do with P means. Okay. Great. That was my tough
Question about that last slide?
Yes. Maybe this is a more succinct. Yes.
Could you go back a slide?
Oh, it's the same things I say.
Well, I was going to say, so minimizing P, power mean welfare, was that referring to the class for P less than or equal to 1 or the entire spectrum of P?
These are short of P. You mean for costs?
Yeah.
For cost P bigger than 1 is what makes sense.
Okay.
Minimizing P bigger than 1. I'm saying no P works, but it's very easy to show P less than 1 for minimizing. Yeah, it's same as it's completely ridiculous to maximize P mean for P bigger than 1 and goods.
Yeah,
it's equally ridiculous to do P less than 1 and chores.
So the theorem also applied to P greater than 1. When you said no,
that's the only place where the theorem has bite. P bigger than 1 for chores is the only place where the theorem has bite. Good. So this is the state of the art. Great. So one can look at this and ask. That was our original question. Is why? Why does Nash have it? So this picture, your instinct is now I'm going to do combinatorial algorithms, to prove EF1 and EF exists. So why does Nash work and others don't? And you can, your first thing would be to look at the counterexample, find an example where others fail. So here's an easy one. It's very easy to construct this counterexample, by the way. Here are 10 items. The first agent has value 1,000 for everything. The second agent has value 1 for everything. So let's see where the other big players fail and Nash doesn't. Egalitarian, so maximizing the minimum. What would maximizing the minimum look like here? You would say, oh my God, like the second person needs to really be made happy. So they should get mostly everything, right? Because the first person, even if they get a fraction of an item, their happiness is equal to the happiness of the second person, right? If they get everything. So egalitarian fails like that. Now you're really messing over the first. Welfare, so maximizing sum. You're saying, oh, the second person doesn't contribute at all. You should give everything to the first person. Right? Well, Nash does it. How does it do it? It's scale invariant, right? Like Nash, which splits half and half in this case, even if you take the first person and multiply it by a gazillion, it will still do the same. And if you took the first person and divide it by a gazillion, it would still do the same. Okay, so scale invariance is crucial, at least in this example. So it's very tempting to say that it's just crucial all the time. So that's the question we ask. So we define this family of functions, normalized P mean, which is exactly the same. I'm just normalizing so things add up to 1. Okay. So this is scale invariant by design. And the first thing is like, what are you talking about? This is a welfare rule. There was this, it's not a welfare function. Yeah, so this escapes the result I just mentioned that Nash is the unique welfare function. This is not a welfare function. It doesn't only depend on UIXI. So it's outside of the definition. Okay. Good. So the question this paper asks is, what can these guys do? Normalize P means. Okay. Simple question. Everyone with me? Good. So let's start with divisible goods. I'm just going to do it one by one. So normalize P means if you optimize them, you get PO and prop. Okay. PO is trivial, prop is not. But for any P less than or equal to 0, maximizing the normalized P mean is Pareto optimal and proportional. Okay. This is not true for any P bigger than 0. And the proof is similar to Nash's, to Haldarian's proof. You can write a convex program, you can take KKT, it corresponds to a market. This market doesn't have equal budgets. The corresponding market solution is not an equal budget solution, but nevertheless, one can show that you can get from. Okay. And efficiency is true. What about indivisible goods? So we show that you can get PO in prop one by starting with the divisible solution and rounding it. Okay, so there's a standard market rounding algorithm that will take this PO in prop and give you PO prop plus one. And perhaps the most surprising result I would say is that for two agents, maximizing any P mean for P less than 0 is PO and EF1. So for any P less than or equal to 0, you get PO plus EF1 for two agents. Just any P mean you want. Okay. Again, not a welfare function. So this is not a contradiction to this theorem. P mean, not a welfare function. Great. What about divisible chores? Almost the same result. So you can't get exact prop, you get an approximation prop. If you minimize normalized P mean for P bigger than 1, you get PO and n to the 1 over P prop. So as P goes to infinity, you get proportionality exactly, but you can do the calculations, right? Pick a P that's like at least log n or something, and then you'll get a constant approximation. And this is tight. This theta to the 1 over P is tight, and it's a similar market interpretation sort of result. So you can do KJT. And for individual charts, exactly also the same picture. You can get these fractional allocations and round them. You get same result, same constant in front of it with prop 1. And again, same as the case of goods. If you maximize over or minimize over indivisible solutions, you'll get PO and EF1 for two agents. Okay. Sorry. Something to observe is that this transition is at 2. So for goods, this was P less than or equal to 0, P less than or equal to 0. For chores, P bigger than 1, P bigger than 2, and this 2 is tight. So there's a bizarre transition that is a mystery to us. Okay, and this is as the first analog of Nash welfare, right? This is we knew how to get PO plus CF1, but not with a non-combinatorial way. This is more of a plug and play. So this is the picture for normalized P means. Okay, so we understand pretty much everything. I'll let this slide for a few seconds. But again, so we can get proportionality for divisible goods. We can round these to get prop 1, and for two agents and indivisible, you get PO of 1. And similar picture for chores. So there's somehow normalizing all of a sudden gives you this unified view that you didn't have without the normalization. Good. So these are our results. So what's open here? Is there an axiomatic reason why all these things are happening? And perhaps more interestingly, I think for me, and I've spent some time thinking about it, is this normalization is the natural one. If I have to normalize, like people do, when people in fair division think of maximizing welfare, they immediately normalize the instance. Otherwise, things are very silly. But maybe there's a normalization that would not stop the good news at n equals to 2. And this, of course, maybe doesn't have so much bite for goods because we're all happy with Nash welfare. But for chores, I believe we don't know PO plus CF1 beyond the case of three agents. So that would have a lot of weight. Of course, you can ask there's many domains where Nash works. Public goods, for example, like normalize there, what happens? I don't know. So that was my talk.
Thanks for the talk. One question, for the indivisible goods, you always find a fractional solution and you round. What happens if you optimize this over an integral?
Oh, that is not true anymore.
Okay. Nothing works.
What?
Then nothing works.
Yeah. I mean, I get FEF1 for two agents, but for three agents, I don't get prop 1 if I maximize over the space of indivisible, yeah. So I'm getting a little. Yes.
So for indivisible goods and the more than agents, you have thought about relaxing EL1 to like EL2 or 1/2 EL1 or these other things, all of them fail or can hope.
Good. My instinct is that they would fail, but I can't say I remember the counterexample if it's robust. That's a good question that I should have prepared for. Yeah. But I believe they fail, but I'll look it up and catch you offline.
I'm not familiar with this, but if you have both, let's say indivisible and divisible together,
Yeah.
so given that you're doing just a rounding thing, can you still guarantee something like this?
Divisible and indivisible together?
Like, you know, the cake with the fruits or whatever, I'm not like.
The what?
Cake with the fruit.
Like you can divide the cake, you can't divide the apples.
I don't know. I don't.
Because you're doing a rounding thing.
Yeah. I'm not sure. I'm not sure at all.
And all this stuff naturally extends from agents have weights,
I don't know that. either.
weighted
Uh,
proportionality, with DF1, all that stuff.
Paritosh was telling me about it. I think Paritosh thinks that's true. There was some
Sounds like
technical,
it would be.
there was some technical lemma that was not trivial to show. One of these things where you need like all the letters of the Greek alphabet, you know, you know, like if alpha times beta is bigger than gamma times delta and this, then is this true? It seemed a little technical. I think he was convinced, but we didn't actually put the effort to write it down. I would not be surprised.
Any other questions? So can you also guarantee something on MMS?
I haven't thought of it, yeah. Yeah.
I see.